Section 3.4 is titled Properties of Logarithmic Functions. And in this section we're going to go over a few different properties that we use to work with logarithms, to rewrite logarithms. All these properties have their equivalent forms as properties of exponents that we're all very familiar with, and I'll kind of illustrate maybe one or two with you as we kind of develop these. So that's this section, Properties of Logarithmic Functions, or just simply Properties of Logarithms. Alright, this first slide goes over the three properties of logarithms that we're going to be using in this particular section. First one is a product property, and it says this: log base b of x times y is equal to log base b of x plus log base b of y. I'm using log base b, I'm using b just to illustrate that b can be any base. But the rule is this: if you have a product of this x times y, then that can be re-expressed as a sum of two logarithms. And again, I kind of explained already that there are exponent properties to all these. The related exponent property is this. As we're all familiar with, if we have maybe, and I'll just give you an example, I think that'll be easiest to see it. If I were to give you, say, x to the third times x to the ninth, we would all say that that is equal to x raised to the 12th. Again, the rule is that, and we all know this rule, we've used it plenty of times, the rule is that when you multiply, you add exponents, right? So those are the two operations that we're using here. It is a multiplication operation, and we've resulted in adding. And since we know that log base b of x is really just like what power of b is this, it's kind of like an exponent. So what this is we're showing that we are adding two exponents together. Okay, so all these logarithm properties kind of have their roots, or have their exponential property cousin over here, so to speak. So I'm going to give you the other two just as log properties, and I'm not going to explain them or reference them like this, but just know that those rules are there, and we know those rules, and that's how we're kind of getting all these properties here. Okay, the next one, quotient property, says that log base b of x divided by y is equal to log base b of x minus log base b of y. Okay, so it's basically just the opposite of the first one. You know, in the first one, if and when you multiply, it's represented by addition. Then this is just the opposite. When you divide, it's split apart as subtraction. Okay, so multiply, add, go together; divide, subtract, go together. This last one, this power property of logarithms, would say this: if we have log base b of x raised to the n power, that's the same as n times log base b of x. Okay, so in this one, the exponent above the x, or whatever you have here, is allowed to move into the front of the logarithm and multiply the logarithm. Okay, so there's our three basic properties, and we're going to use those properties on, I believe, every slide, every problem that comes as examples in the rest of this section. Okay, the directions on this first problem say expand the logarithm of a product. So what we're trying to do is write this single logarithm. We have one logarithm, right? We're trying to write this single logarithm as multiple logarithms, okay? And we're going to expand this everywhere we see the product. So here we've got a product there and a product here. And so this is that first property, that product property illustrated. This would expand this way. Log 144 plus log x to the fifth plus log of y. Okay, so there it is. What I've done is everywhere I've seen a multiplication has been separated with an addition. Okay, that's that product property of logarithms. Now typically what you see, anytime you see log expressions that deal with exponents, you see those exponents brought out. So you probably see this one finished this way. Log 144 plus 5 log x plus log y. Okay, so there's the problem rewritten or re-expressed as multiple logarithms. And it's a very, very useful skill to be able to do this, especially as you'll find next year when you take calculus. It's very, very useful to be able to take complicated expressions like this one here and simplify them to much simpler expressions. You would probably all agree with me that 144 is simpler than 144x to the 5th y. And so is x much simpler than the whole thing, and so is y. So we're taking complicated expressions here and re-expressing them into more simpler expressions. We have more of them, but more terms, but they're simpler each one. That's kind of the idea. All right, another example. This one is expanding the logarithm of a quotient. So here we see a division, and whenever I see division, that's going to get separated with subtraction. So I begin this with natural log square root x plus 1 minus natural log x squared. And just like I did in the last problem, any exponents that I see are going to move to the front of their respective logarithms. Now remember, a square root is a power. A square root is a 1/2 power. So this one becomes half natural log x plus 1 minus 2 natural log x. Okay, one more slide that's got a couple of problems on it of the same directions that we've been doing, expanding the logarithmic expressions. This would be a good opportunity to pause the video and try the problems on your own, and then resume the video after you've done them, and you can watch and hear my explanation to each problem. Okay, this first one, I've got a division, and then I've also got a product down here. Now there's two ways to think of this product, and I'll kind of explain them both. This is going to be log base 2 of x squared minus. Now I can do it this way. Since both these are in the denominator, I'm subtracting this entire expression. Log base 2 of 3 plus log base 2 of y. I've used plus because of the multiplication right here. However, this negative, this subtraction, is going to have to distribute to each term. So this really becomes log base 2 of x squared minus log base 2 of 3 minus log base 2 of y. I typically skip this line right here, just go straight to this. I go ahead and put a subtraction on each of them because I'm dividing by each of them. But either way you want to start, you can get to the same thing. Now all I do is rewrite this first one as 2 log base 2 of x, so the power just moved to the front. This one has no power to move, and this one has no power to move. And that's finished. Okay. Second one does have a power to move. It's a big square root, and that big square root is a big 1/2 power, so I'm going to move that first. It's half natural log x plus 1 over x minus 1. Okay, so what do I have? I've got half. Now I'm going to split this up. Natural log x plus 1 minus natural log x minus 1. You could probably leave it like that if you preferred to have that 1/2 distributed to each of these logarithms. Well, you could certainly do that. And that one's finished now. Okay, this next problem You see the directions have changed now. They don't say expand anymore, they say condensing a log expression. Well, it would make sense, hopefully it would make sense to you, that if we can take a single logarithm and pull apart into multiple logarithms, then we could take multiple logarithms and put them back together into a single logarithm. And that's what condensing means. It means put it back together as one logarithm. Well, so what I'm going to do is begin the way I ended the last problems, is any exponents or any numbers that I see in front of the logarithms are going to go back as exponents. Okay, so this could be natural log of x squared cubed minus natural log of xy squared. That's the same as natural log of x to the 6th minus natural log of x squared y squared. So I've just worked with the powers. Okay, now let's combine these two logarithms into one logarithm. Since they are being subtracted, that tells us how to combine them. A subtraction is going to be combined with division. X to the 6th divided by x squared y squared. And since I can reduce these, I'm going to go ahead and do that. It's going to be natural log of x to the 4th over y squared. And finished. Alright, last thing I want to go over with in this section dealing with logarithms is a change of base formula. It can be useful whenever we have problems like this. Say I was asked to evaluate log base 3 of, say, 29. Okay, now, I'm not quite sure what that is. I could estimate it because I know that 3 cubed is 27 and 3 to the 4th is 81. So I know that the answer to this lies somewhere between 3 and 4, because 29 is something between 27 and 81. The question is, what is it exactly? And so we've got this change of base formula that will allow us to do problems like this when we encounter them. Change of base formula is this. Log base A of x is equal to log base B of x divided by log base B of A. Okay, so we're allowed to change the base of the logarithm to any base we want. Okay, it can change to any base that we want. Okay, so if I wanted to work this out, I would do it like this. I'm going to change that base to a common log, or I'm going to change that base to a natural log. Why? Why might I do one of those two logs? And the answer is that those two logs can be evaluated on the calculator. And we've got buttons for those. So for example, if I were to type in log 29 divided by log 3, or natural log 29 divided by natural log 3. See that the calculator doesn't discriminate. It doesn't matter which base you change to. Same value either way. Okay? And that value falls in line with what I would estimate the answer to be. Just a little bit bigger than 3 is the answer to this problem. And that's what should have happened, because 29 was just a little bit bigger than 27. So this gives us a way to evaluate logarithms whose base is such that it's not on the calculator. We can do it this way. Okay, so last two examples, and they say evaluate by changing the base. So log base 5 of 12 is equal to log 12 divided by log 5. And if I type that into the calculator, I get this to be about 1.54, we'll say 40. I'm going to use 4 decimal places there. Okay, and of course I can use the log, I can use natural log. So log base 9 of 45 could be natural log of 45 divided by natural log of 9. And so this is 1.7325. And that's finished.